All right, let me quickly set everything up. Hello, everyone. Let me get everything set up on Zoom now. Oh, I'm not actually properly signed into Zoom. One second, I need to leave this meeting and rejoin. Apparently I need to two-factor authenticate. All right. There we go. And that's sharing now. Let me make sure I have the chat open. Okay. So what are the current questions on this module? Let's see how people are doing so far. Yeah, I can hear you. Okay. Yeah, so let me try and pull up what you're talking about. So you're looking at level 2. Let me run that. Actually, let me run it in practice. Just in case we want to attach with GDB, which we probably will. Okay. Mm-hmm. Input output error. The error shows up inside your GDB. Yeah, I'd have to. Let's see if we can reproduce that. I haven't seen that. Unless, actually, maybe I know what you're talking about. Let's launch with tmux. So you're talking about maybe when we launch up the challenge. Are you talking about this right here? This can't access TTY job control turned off? Was this on level 2? So the issue might be, and I haven't tested this, is that level 2 the device doesn't have a read option or a write. Right, yeah. So if I do, what am I doing there? Yeah, so you're talking about this. Yeah, so there's no operation defined. Yeah, so I guess the kernel just generally says like, hey, no, you can't do that. Yeah, exactly. Yeah, so if we look using objdump, and actually something potentially useful that might at least kind of address what you're talking about. Let's see here. Let's pull up the default view using objdump. And if we look at, like, say, IO control, where is that? Why device? Huh. Okay, whatever. We have it here. I don't know exactly what's happening there. So you're talking about these calls then? How it seems like what is this call 45? Yeah. So the thing to realize actually is if you look over to the left, with the actual raw bytes, is that a lot of things here will just have a bunch of zeros. Like several things that are referencing what you might think of as like symbols or referencing some other external thing actually just have a bunch of zeros there. And the reason for that is that those zeros are going to get filled in when the program links in. And you can actually see this with objump as well. If you add like a -r, or like you can make it -dr or whatever, this will show you the relocations that are going to happen. So if I go in here now, you see these extra things showing up. So this basically tells us here on this instruction that these 4 zeros are the 32-bit value. This 32-bit value is actually going to get filled in with .ro data .stir1.8 plus hex 80. And then you can... Exactly, it gets linked in because this is just a shared object that the kernel loads in. So for instance, we don't have a print k function actually defined anywhere in this module. That's actually a kernel function that's available, and it doesn't know where it is until the kernel goes and actually links it in. So this call instruction here is actually going to end up doing a call to print k, but when you just do objdump without looking at the relocation symbols, it's just a bunch of zeros and looks confusing. But with the that just threw things off. Maybe that's better. But yeah, with the relocation symbols, we can see that it's actually going to be calling print k, for instance. Yeah. Yeah, so GDB would definitely make things easier, but if you do want to statically try and understand what's going on, I would definitely recommend either use a tool that will actually handle these relocations. It doesn't seem like Binary Ninja Cloud does a very good job at this. I think I looked at R2's Cutter tool, which is like another thing, and it kind of does it, at least in the decompilation. It seems to understand the relocations, and I didn't get a chance actually to look at Ghidra. Maybe Ghidra will handle these relocations better. But yeah, it might just be easier to use GDB. And as a refresher for everyone watching for how you might actually go and use GDB, let me make sure when I adjusted the size of this screen that I didn't mess everything up. Maybe that made things worse. Hold on, if I do that. Now let me quickly just close my terminal since I resized it. I don't want it to be messed up for the next hour. Yeah. Okay. And let me zoom in. Okay, so as a refresher for people watching on how we can use GDB to analyze this sort of thing, we want to run the challenge in practice mode, And once we are in practice mode, you probably want to launch something like tmux, or you want to SSH in two different terminals on your computer. So the first thing you need to do is launch, and then that will make it so that this first terminal that we have access to is kind of in the emulated environment. And then in our second terminal view, we want to gdb opt pwn.college kernel or Linux 5.4 VM Linux. And then we can do target remote 1234. And I guess pwn.debug might have some issues with this. And maybe I actually want to turn pwn.debug off because, well, maybe it's kind of readable from this stream. I can kind of see what's going on. Let's try it. But now that we're in GDB, we are frozen. I guess you can't exactly tell, but I'm spam hitting the enter key and nothing's happening inside of the terminal. And that's because we're currently broken inside of GDB. If you just typed, for instance, continue, now you can go back to using your environment. So how we would be able to start looking at, so I guess the easier thing to look at first would be it would be when we do a read on the device. So if we do head-c20, this will like basically print out 20 characters. You could also use dd, which probably makes a little more sense, but this works. Proc pwn.college. So we can see that it read out the password twice, because I guess that's kind of 20 characters worth or whatever. If we wanted to now look at this in GDB, we would want to do tail proc k-all-syms. This will tell us the most recently added symbols into the kernel. We are interested in this case of looking at device read, which is located here. And we want to, you can hit Control-C inside of GDB to just like basically force it to break. And then we can do, actually I just hit enter, which re-executed the last command and continued again. Let me hit Control-C again there. And then, so if we break at that address that we copied, and then we can continue. And now if we have the ability to interact until we hit that breakpoint, and we will hit that breakpoint if we do this, this thing which we'll call read on it again. You can see it didn't print out as many messages as before, and currently we're broken. So if we switch back in, we can see, oh, and I turned off, maybe this isn't the best way to look at it. Yeah, let's turn off pwn.debug. I think that will be the easiest way to do this. So we can just move gdb init to gdb init.old, and then we just won't have a gdb init. And then we can do, we execute our command that we did before. And we can do target remote 1234. And now we are just in vanilla GDB, which might be a little bit easier. We were already seeing some weird bugs in pwn.debug, like this could not find elf base, because pwn.debug is trying to do all sorts of useful, helpful things. But our current GDB environment's a little more complicated than a normal program. So we can do, I actually haven't used this much, but I think this is what I've seen Jan do. Display 8 instructions of RIP, and then we'll just like basically always be able to see this. Oh, this is terrible. We don't have Intel. What is it going to be? It's like set disassembly flavor or something. Let's just guess it. Disassembly flavor Intel. Let me quickly Google it. GDB disassembly Intel syntax. Set disassembly flavor. Did I misspell it? Looks like I maybe did. Oh yeah, one S at the start. Okay. Intel. Okay, so now if we just quickly look at 8 instructions, we are looking at sane Intel syntax. And then, so we're currently still broken inside of our emulated environment, but we can start to see what's going on. Actually, we're broken at default idle, which basically means it just like immediately broke when we entered into the GDB session, which is okay, but we need to reset up our breakpoint because I guess it's stored in the client, not the server for GDB. Let's do device read. And then let's set that breakpoint. And if we hit continue, we should probably see that the first read triggered. Oh, maybe they both did. But we can just execute that read again. And now we are broken where we want it to be. Okay, so we can see, in fact, we can actually create a third terminal inside of this tmux session to look again at that obj dump. Obj dump -d rm intel, and then device read. Why is my search failing? Whatever. Device read. Okay. So we can see that it starts with this like push R12, R8, R12, RCX, RBP stuff, and we can see exactly the same in GDB that we have those same instructions getting ready to execute. If we wanted to see, for instance, actually let's just start stepping a little bit and seeing what's going on as we perform this read. So we know experimentally we've seen that this will, like, for instance, print out the password to us. So maybe we can understand how that's happening. So if we just start stepping, and it steps a lot faster, I guess, in vanilla GDB because, like I said, pwn.debug is doing all sorts of helpful things for you that I guess are slowing things down. So maybe you will want to use vanilla GDB in this example and just use these display commands to make it so you can just like always see information you're interested in. We can just start stepping and seeing if we can see like a string get loaded at some point. Basically, we're looking for like a large address to get moved into a register. And we can see one coming up, that some large address is getting moved into RDI. So now if we do x/s RDI, we can see this is actually the debugging walkthrough information that's telling us kind of what's going on with what's getting passed into this read call. So let's just keep stepping and kind of taking a, so we don't actually, if you wanted to, you could actually step all the way through this printk function, but we're not really interested in understanding what printk does. We'll assume it just prints. And then we can keep stepping. So we can see something else is getting loaded and it's rip relative, which means it's going to be something, some sort of data in like the globals or something of this kernel module. So if we step here, and we saw that it moved it into AL. So let's see what AL is. It's 0. So maybe it's kind of hard to tell, but we can actually see that we're about to compare that with 2. So maybe that value being 2 would mean something. And if we've looked at kind of other things, maybe we know that this is our variable for representing where we are in the kind of this state machine that this device stores for keeping track of if we've sent the right password. So we can see another string, or what seems to maybe be a string, is about to get loaded. If we do next and then XS RSI. In fact, we can actually see, this is of course we're running in practice mode, which is what allows us to use GDB. But we can actually see that this is responsible for loading the flag in. And presumably this control flow is going to dictate whether or not that'll end up getting printed to us. So if we continue stepping, we can see that we did not take it because we were about to go to 572, but we are not executing at 572. So, and looks like this was stored in RSI, but now something else is about to get loaded into RSI, and we never actually called print K. So clearly we're not going down the control flow that we're interested in. If we look now at what is in RSI, we can see unknown state. We didn't actually see that get printed to us, so maybe it's going to get overwritten again with another control flow thing. If we continue stepping, we can see that yet again another string is going to get loaded in. So some sort of weird, it's a little confusing why the compiler chose to generate code that's just like constantly loading different strings in, but I guess it did. If we step again, we will see what is in RSI. And like, the thing to realize is that even though these strings are getting loaded in, nothing is called print K to actually print these out at any point. So let's just keep stepping. So now we have password in there. And where are we? Something's about to happen, but let's just keep stepping until maybe we see. Okay, we can see that we're in this like repeated prefixed instruction that I don't exactly know how it's going to work. But let's just go ahead and continue all the way to this call. If we break there, hit continue, we can see that now we're about to copy some data to the user. Presumably that will follow standard calling conventions with RDI, RSI, etc. So let's take a look at our registers. Interesting, that was maybe not the best idea. Let's just go ahead and manually print what RSI is, and print what RDI is, and even print what RDX is. Okay, so let's see then what RSI is as a string, because that looks like it's going to, it's some address, maybe it's a string, it's about to be copied to the user. And yeah, that's still our password variable. We have this RDI value that it's pretty unclear what this is exactly. But if you looked into the documentation of copy to user, you're going to see that it is effectively just like a mem copy, but does some permission checking along the way. And we're going to be copying basically from kernel space this like high eft value address, which is kind of the pattern to keep in mind when working with the kernel, is that similar to how like the stack is like this shorter address with like 7F and then some FFs or whatever, kernel addresses often start with like a bunch of Fs at the start. So we're copying actually from kernel space to user space. So this program that we ran, head, of course, is executing code. It has some buffer that it's going to read that data into in order to then send it out to standard out. And that's probably what this buffer is. So if we, I guess it's not exactly, let's take a quick look to see if we can, if we dereference it, we can see we actually can dereference it, that this is addressable memory. And it does turn out that it is in user space. So we can actually see if, and then also this third argument is probably going to be like 10 characters. We're going to copy the length of this string. And again, where we currently are looking at is this call. If we jump over it and then take a look at this, what we're calling and assuming and technically knowing is a user space address, when we finish up this call, we can actually see in user space that if we now look at this address with xs, x/s, why is it not copied? xs, there we go. I can actually see that this string got moved. It was basically a mem copy with permission, or it basically makes sure that you're not doing the mem copy into kernel space. You can kind of think of in the kernel, you need to do a lot of secure code, because if you destroy the kernel, like you destroy everything. Or if you get memory corruption in the kernel, you just own the system now at that point. So the standard, there's a lot of standard functions that get used as part of writing secure kernel code. And one of those things is copy to user, which is effectively a mem copy, but it will make sure that you're not doing a mem copy from kernel space to kernel space. You could imagine that when someone does that read syscall, when head does this read syscall, if they wanted to be malicious, you could imagine that instead of passing their user space address, they could actually pass a different kernel address and try to convince the kernel to move data from one part of the kernel where it like makes sense into a random user controlled part of the kernel. And if you could do that, you could potentially start overwriting data structures in the kernel. And now the user space program is basically would be allowed to control the kernel's memory, which influences the control flow, and it could escalate privileges. But we don't use a mem copy. We use a copy to user, which basically just verifies that this is a user space address, that we're not being tricked as the kernel into copying memory from kernel to kernel, which we really don't want to do as the kernel, because that's how we get owned. But that's kind of, I guess, a side tangent. So yeah, you can look at this to understand what we want to do in this program from two perspectives. You can do it statically. You definitely want to be aware of these relocation symbols if you're going to do it statically, or you can do it in GDB as we just showed. And you could probably reverse now the IO control program and see, or the IO control device handler, and see what control flow is in there that would allow you to print out the flag. We saw clearly that this device read has some capability of loading the flag into a register. So presumably with influencing the state machine of this device, you could probably convince it to print out the flag. Very similar to the first level. Okay, so what other questions are there for this office hours? Yeah, go for it. Yep. Right. Yep. There's, yeah. That's not exactly true. So the question is related to level 4. Let me go ahead and launch level 4. Let me get out of this TMUX session. So if we take a look at level 4, we will run it in practice mode. Eventually. There it goes. Okay. So if we start up in TMUX, let's just begin by launching the VM. Oops. And create another. Let's create 2 more again so that we can have one for ObjDump, one for GDB, and one for the emulated environment. And then let's go ahead and do ObjDump here. -dr-m intel. And we discussed that there is a device write. I still don't know why this isn't searching properly. I don't know if it's a TMUX thing or what. Device release, device open. Hold on. So we can definitely see that there's a device write. Yeah, it's unlikely that it'll be related to the initialization or the deinitialization of the module. I still don't know why I'm not able to easily use objdump here. Let's just scroll though through all of these nops. Yeah, so if we take a look now, oh, this is like weirdly destroying my terminal. I don't know what's going on here. Anyways, if we take a look at device write, as you said, there's no comparison. So there's not really a direct control flow involved. But let's see what some of the things are that get called. We can see that there's a copy from user that's going to actually get called. So presumably we're going to write data to it, and in order to write data to it, it's going to copy that data we're sending, and it's going to put it somewhere. It's going to put it, it seems like, on the BSS. So it's some global data structure. And then, so that's the 2, which is RDI. That's where it's going to write, that's where it's going to copy to. Where is it going to copy from? We can see RSI gets influenced by RBP. And RBP gets set by RSI. So RSI being the second parameter into device write. So somehow, which the second parameter to device write will be the buffer, because the first parameter is the inode, which you've seen kind of in this walkthrough when it prints out. So actually, let me just show it rather than kind of sit here and kind of guess through what's happening. And it's going to be a little unfortunate what's about to happen, but we'll go with it. If we echo A, because we're looking at this device write, so we want to write to the device and see what happens when we do this. Can I scroll? Let me go here. So we can see that device write, this is in the walkthrough mode, it's kind of printing everything out to you. I guess it's not an inode, it's just a file struct inside the kernel here. We can see that this first parameter, which would be RDI, is this kernel address or whatever. And then the second one looks like it's a user space address, which is the buffer. So when we were looking in objdump, we can see that that second parameter RSI gets moved into RBP, and then nothing happens with RBP until here. So I guess something to note as a kind of maybe slightly side tangent here is that by default these kernel modules are going through the default, the way we build these kernel modules is going through the standard kernel module makefile, which is using optimizations to optimize the code. So in past challenges that you've seen we just run GCC basically to compile the challenge. We don't introduce any optimizations. So part of the reason, as you're reversing these kernel modules, that it might kind of look especially different from things that you've seen in the past, is because this is actually optimized code. I'm not actually sure what the default settings are with when building a kernel module using their make file, but it's optimized at least at some level, and it's probably very optimized because that's probably just like the default settings. So we're not actually using RBP to represent like our stack, right? This doesn't make any sense when we do this operation. So I guess we're still saving RBP because maybe the caller wanted to use RBP or whatever. I'm not exactly sure the semantics of needing to save this, but we probably need to save it just to be safe or whatever. Maybe we're gonna be called by some unoptimized code. This is probably part of the calling convention probably says we need to save RBP. But beyond that, we can see that RSI, which is our second parameter, is actually getting moved into RBP, which clearly makes no sense if this is supposed to represent our stack. RBP is actually just being used as a general purpose register. So that's kind of a side tangent here on why things might look especially different. So if we keep looking, actually we can see there is a comparison involved, but maybe that's not exactly a super useful comparison. So anyways, we can see that RSI gets moved into RBP, and then the very next thing, as we track through the dependency on RBP through this code, we're kind of looking for the next instruction that involves RBP. But we can see that RBP gets moved into RSI. And so that looks like it's setting up for a function call, which it is. It's getting ready for this copy from user function. So RSI gets set with our user controlled thing, which is the second parameter, which is where we're going to copy from. So this is our user space address getting ready to be copied somewhere. And then the first parameter to that copy from users is RDI, which, as we said, is going to the BSS. It's some global variable inside of this kernel module. So we're about to copy from user space to a global variable in the kernel module. And then somewhere there should be our third argument, which I don't exactly know what cmoveBe does, but maybe we can just sit here and pretend it's a move for our purposes. And if that assumption is wrong, it's probably something different than a move. Otherwise, they would have just used a move. But let's just pretend it's a move. This is setting up our third argument. And that is coming from RBX, which looks like it's going to be a size thing based off this comparison maybe, and the fact that, yeah, go for it. There's a question. Yeah, so the reason it doesn't show anything about the BSS is that you need to add a -r flag to objdump. That'll show the relocation symbols. So a lot of this code, as I mentioned at the beginning, has like basically these quadruple zeros, which is basically just waiting to be filled in when this kernel module gets linked into the kernel. These values will actually just get updated as part of linking it in. They'll just be completely changed. They'll be relocated. Yeah. So once we turn on relocation symbols with that -r flag to objdump, we can see basically right below the instruction, we have these 4 zeros. We can see that those 4 zeros are going to get filled with this symbol, basically, where this symbol is like part of the BSS. So we can see that we're about to copy from user space to some global variable in the kernel with, I don't know, something to do with 1,000 or maybe some user controlled value or who knows what, but we're going to copy some number of bytes from user space to kernel space. And we're going to copy it to this like BSS thing. And then what happens next? We can see the result of that, which maybe doesn't matter, gets stored. Maybe that comes up, maybe it doesn't. You could look into what the result of this is, but maybe that doesn't matter. then we can see that this global variable, that this BSS plus 4 is getting loaded into RAX. And then we do this call right here. We call x86 indirect thunk RAX. So that might sound like some insane function name. What is an indirect thunk? And it'd probably be worth it to kind of Google for the idea of thunk as it relates to computing. But the short story is it basically just calls RAX. So this is it does some checks or whatever and does some setups. If you've heard of, I could be wrong on this, but I think it probably would have done a call RAX if we would have compiled this like a year or two ago. I think the reason they introduced this thunk RAX has to do with if you've heard of Spectre, that like CPU flaw. I think they introduced this to, I think instead of doing a call RAX, they do this call indirect thunk RAX thing as a Spectre mitigation, as a little side bit. I'm not 100% sure on that, but I'm pretty sure I was Googling around for that, and that's why this is being used instead of just a standard call RAX. But either way, moral of the story is that we're calling into this global variable. So data is getting stored. We're copying from user space data to a global variable, and then we're just like calling it. So if you think back to like the shell coding module, this should be familiar to an extent. And yeah, so in fact, we can actually see, we can kind of see that if we, oh, this already crashed into it. But maybe we can scroll up. We can see in the walkthrough information that kind of tells us what's going on in this challenge. It actually very nicely tells us that, and confirms our suspicions of what's going on here, is that this character device will execute any shellcode that you write to it inside the kernel. So maybe now this might make more sense why I was a little hesitant to write echo A to this, because it crashes the kernel. It literally is going to write A into this global variable and then execute it. And as it turns out, A is not a very good instruction. A will crash the kernel. And if you're not careful, a lot of things will crash the kernel, right? You need to write correct code, I guess is one way to put it, to not crash the kernel. So something simple we actually can send to the kernel to make it not crash. If we relaunch the kernel, since as soon as you segfault crash the kernel, it's done. You've got to just relaunch, which is kind of an interesting thing. So like in the shellcoding module, you crash the process, it's no big deal, it just segfaults. If you crash the kernel, like that's the final defense. I mean, I guess maybe you could consider the hardware being the real final defense in terms of not destroying your system, but from a software perspective, the kernel is the final line of defense. If you crash that, it's game over. So we relaunched. If we take a look at something we can do. So if I switch into this session, let's take a look in IPython. What is happening here? What? Yeah, there's a follow-up question. Go for it. I am not entirely sure on that. I don't exactly know what it would do. Yeah, I think you're going to find that if you just do a syscall instruction in the kernel, it will crash. There might be a way to make it work. I don't actually know exactly. So I can tell you for sure that if you just try and do like your default send file shellcode and send that to the kernel, that it will crash. I don't exactly know what the mechanism is at play that makes it so you can't do a syscall while you're inside the kernel, because in theory, I would imagine it should interrupt and then go into the kernel, re-enter the kernel into the syscall handler table and start executing syscall handler code. But something along the way crashes, and I'm not exactly sure what. It might be because the kernel doesn't have like. No, but that doesn't make sense. I don't know. I really don't know, but no, for all intents and purposes, it's going to crash. You might be able to find a way to make it happen, though. But yeah. But something to realize is that while you're executing inside of the kernel, you have access to all of the functions inside the kernel. So even if you can't do a syscall instruction per se, and what I'm about to show you isn't actually the easiest way to go down this. I don't actually know how you'd write code to make this happen. But for instance, the send file syscall will actually end up calling do send file in the kernel. Let's confirm that. Proc k. Yeah, go for it. Yeah. Mm-hmm. Yeah, so if you're looking for like chmod and stuff like that, you'll find related kernel calls because when the syscall happens, it's just going to hit a syscall handler table, and that syscall handler table is just going to call a function that exists inside the kernel. So, like for instance, when you syscall send file, that syscall handler table is ultimately going to just basically end up calling do send file. So you could call do send file yourself instead of do a syscall instruction. The issue though is I don't exactly know what this would look like, honestly, if you were to try and make this happen. It would probably be more tricky than it's worth. But what Jan talked about in his fourth video on kernel modules is two functions in particular. There is no, I'm forgetting the second one, what it's called. One of them is called commit creds. And the other one is something to do with like create new creds or something. What's it called? Commit creds. Totally blanking on what the second one is called. Prepare kernel cred. That is the name of the second call that matters. So if you haven't watched the kernel module videos, I'd highly recommend watching them. Prepare just to show that this exists inside the kernel as a symbol. Okay, apparently. Yeah. Yeah, and I can expand. Oh, it's not plural. Yeah, okay, so there's commit cred and prepare kernel cred. So the way it works at a somewhat of a high level and I guess also simultaneously low level is that in the kernel you have this concept of a creds struct. And this creds struct basically, ultimately it says kind of what your permissions are, who you're executing as, blah, blah, blah. I think maybe you probably want to look into it deeper. I think I might be quasi-lying on that. But basically, if you do prepare kernel cred on 0, it will prepare a creds struct for the root user. And when you call commit creds, it will apply the creds struct passed to it to the current running process. And the current running process is still that process that invoked into the kernel code. So if you think about it from the perspective of if you run, let's say, the syscall get effective user ID, which is a syscall, get EUID or whatever, that will tell you what your current effective user ID is. And the way that works, basically, is that the current running process exists in the kernel as a task struct. So the kernel uses task structs basically to represent the idea of a process. And the current running process, I believe, is called, inside the kernel, there's like a global variable or something just called like current. So current is the current running process's task struct. And this kernel code that starts getting executed, for instance, when you call into the kernel with get effective user ID, it will actually use this task struct, the current task struct. It will, and it'll access some member, and I would definitely recommend reading more on this if you're interested in this sort of thing. One of the fields inside of a task struct is the creds struct as well. I believe creds must be a struct or a pointer to it's a pointer to a struct probably. And so the current running process basically has a creds associated with it, which basically defines what its permissions are. So when you start accessing files through the kernel, like you have to do an open syscall, it can basically consult with that current creds struct and see whether or not you actually have the permissions to access that file. And it knows whether or not you can access that file because that file has metadata on it that basically says who it's owned by and what the permissions are for it for people that, for the user ID that does own the file, or the group that does own the file, or other people. It can basically just consult the creds struct as well as the metadata on the file to see if you have permissions to open that file. So anyways, that's kind of a side tangent again, lots of side tangents in this office hours. But what I'm saying is that commit creds is going to apply basically what your new permissions are, what your creds are for the current running process that invoked into the kernel. So if we prepare kernel cred with 0, that will basically prepare a new creds struct for the root user. And then if we commit that, it will apply that to the current running process. So in doing basically what's in C would look like commit creds prepare kernel cred 0. If we do this sort of call, and you could imagine writing this as shellcode, for instance, it will make it so that the current running process now is running as root. So something though to keep in mind is that it is the current running process that is running now as root. There's not really the correct way to think about permissions is that they are metadata on a process. When you're running in the system as this CTF user, I guess we're currently running it. So when I type who am I, right, it says CTF user. That might be a little misleading. Maybe, I don't know. It kind of depends how you're thinking about it when you see that I am the CTF user currently running. There's not really a user running, right? All I am is this process. So lsal proc self command line or whatever, right? Cat. No, let's do, yeah. So I am this sh process, right? I have a PID. I am PID1 currently, and I'm executing. PID1 is just, it's a process. Everything is just process. So in the same way that a lot of things, everything is just like a file. Running stuff is just a process. So that process has permissions attached to it. There's no like user running the system or whatever. It's just that this shell has the permissions of CTF, has the permissions of user ID 1000. You could imagine that the task or the current task struct has this creds field attached to it, and the creds is pointing to some pointer that basically says I'm user ID 1000. And then when I go and do Oops. Then when I go and look at this flag file and call into the kernel and do cat flag and it tells me permission denied, what's happening here is it says, okay, you're process ID 1. You're going to create, and you're a shell. So that, I mean, as a shell, like you're basically just going to start forking off new processes. I'm going to create this new cat process. This cat process is going to inherit my permissions because it's not setuid, for instance. It's just kind of this normal thing. It's going to inherit my permissions. So it's going to, its task struct is going to have a creds field, and that creds field is going to say basically, hey, this is user ID 1000. And now cat is running. And when cat tries to open this file, it's making an open syscall. That open syscall is going to, it knows what the current running process is. It can look at the current, it's called current as like this global variable or whatever that is the current running process, which is a task struct. It can index into that task struct to get the creds field. It can check with the creds field to see what user am I, or what's the user ID, what's the effective user ID, what's the real user ID, whatever it wants to consult. And it can look at the metadata on this flag file, which is backed by some inode, which is kind of like this metadata and data of the file attached together. And it can basically say, okay, well, am I the current, do I have the permissions? So the way to think of it, am I the owner of this file? The user ID of this process, is it the owner of this file? And the answer is no. Well, do I have the group? And then the answer is going to be no. So then we're going to look into these last 3 bits. Okay then, so if I am an other, according to the current task struct, looking at the creds field and comparing with the metadata of this file, so I'm the other. Okay, well, do other people have the ability to read? And the answer is no. So it returns out false. The open syscall basically just returns some error. Cat interprets that error as permission denied because this is like a well-defined interface. And then your shell reports back, or I guess probably in this case, cat reports back to you permission denied, and then the process dies, and now we're still back in our shell. So all of that is to say that I'm not a user. It's just, everything is just a process that has a creds attached to it. And why this might matter to you is that when you go and commit creds of, when we go and do we have this in our history? Maybe we didn't say it, save it. So we have prepare kernel cred, and we have commit creds. So when I write shellcode or C or whatever to do the equivalent of this, prepare kernel cred 0 and commit cred. So I'm going to be running this in kernel space, but this function call presumably will basically look at the current global variable, which will basically allow us to know what our current running process is, look at its task struct, and basically change the creds field of the current running task struct. And it will make it so now it is root. But as I said, the user's creds are just attached to the process. So if you elevate the privileges of that process and then you go on and just let that process die, it's not like suddenly your shell is going to become root. It's the current process that ran this code that becomes root. So even if your child process ends up becoming root, it's not like your parent process also gets to become root. It's not how it works. Credentials are inherited, but they're not like fed back up into the parent or something weird. So which is to say that whatever process becomes root, only that process became root. It's not your user didn't become root, like CTF isn't now able to do root things. No, just the current running process has the permissions of root. So then there's a question in Zoom chat. So if the process also calls execl bin sh, would bin have root privileges? Yes, it would, because yeah, exactly. So if you call now bin sh will be a new child process that gets spawned out of this root process, and it will inherit its creds. So if you're able to inherit it, then yeah, now you have a shell running as root, and then if that shell calls cat, that will create a new process, which will be a child, and the privileges will be inherited by cat. So yeah, it will feed downward, but it won't like propagate back upward. So just keep that in mind when you elevate your permissions. Maybe this is more, maybe too in depth on kind of why all of this works in this way, but I think it's important to understand how these things work at like a basic level. Especially when you're working in the kernel, all of these things are actually, I don't know if like simple is the right word. Yeah, maybe simple is actually the right word. Maybe you don't immediately know how these things work, but when you look into them, they're actually pretty simple, right? It's just like a bunch of structs and pointers, just like saying things. I don't know. So yeah. Yeah, so let's see, is there any more questions here on this after this like fourth tangent of explaining kernel stuff? Yeah, go for it. No, go for it. Anyone else can chime in whenever they want. So yeah, and 5 is similar. It allows shellcode to execute, but there's going to be, the first twist is that you're not writing it to the device, you're using IO control. And the second twist is that some, I would say, as basic as we could make it, reverse engineering will need to take place. What I mean by that is that it's not just your, so whereas in this challenge you're just writing shellcode and that shellcode gets executed, in level 5 shellcode is involved and shellcode can be executed, but it's not just send shellcode, it gets executed. It's slightly more complicated, that basically IO control is expecting a specific arrangement of memory. And you'll have to look into how that memory is being accessed to understand what it is. Yeah, so some level of reverse engineering will have to take place, but hopefully it's not too bad. It's basically I don't know, like 20 assembly instructions worth of reversing to understand and kind of parse out what the memory layout has to be in order for this thing that you're passing to it. The idea with level 5 is basically we want to make sure that people are familiar with this idea of structs, and that often when you're working with these low-level concepts, there's lots of, it's not just 1,000 bytes of shellcode being sent somewhere. Often it'll be a struct being sent somewhere that has several fields. And even if you don't implement it directly yourself as a struct in C and then like create this struct and pass it, you have to understand how the arrangement of memory looks like, which is what a struct is. Okay, there's a, yeah. Yep. Awesome. Okay, so there's a question in Zoom chat. Is RDI usually arg1 for most kernel functions, or is this something we would have to navigate with GDB? Yeah, so the calling conventions still apply. RDI will be the first argument, RSI the second, RDX the third, and so on. I don't actually know what the fourth one is, if it's R10 or RCX. So if you think back to, I don't remember which modules it would be, but something to note is that, for instance, when you're writing C code and it gets compiled down and follows the standard calling convention, there's kind of like this function level calling convention versus this syscall calling convention where the fourth parameter is different. I would assume that it follows like the function-based one where like RCX is the fourth, but maybe you don't even need to pass the fourth parameter. But yeah, you can Google for the calling convention, especially if you do need to pass a fourth parameter at some point. In order to pass parameters, we put up to 6 of them into registers: RDI, RSI, RDX, RCX, R8, R9. Yeah, I would expect that to be true. I would be very surprised if that's not true. Yeah. Okay. So, oh, and right, I just wanted to show also for level 4 to just show that we can make it so that we don't crash the kernel. Though IPython, I don't know if IPython hates tmux or what's going on here. Maybe Python can handle tmux? It can. Great, let's just use Python then. Pwn context arch equals AMD64. And then let's use pwn.asm. All we want to see is what a ret looks like. C3, right. Okay, and the reason I'm showing you this is that in level 4, as I said, if at any point your shellcode crashes, the system crashes. And that means that if you don't, since we're calling into the shellcode, if you don't pass like a ret at the end, the kernel will just crash, which is something to keep in mind. And we can actually see that if we only send a C3 to the device, that the system won't crash. It'll just call our shellcode and immediately return. So if we do echo -n for no new line -e to interpret escaped values, basically, so we can do /x, xc3, and we send that to pwn.college on level 4 here, we can see that we did not crash the kernel. The device driver, the kernel module, called into our shellcode, and we just immediately return control back to the calling code. Okay. So are there more questions? And yeah, are there more questions? If there aren't, maybe something I can show real quick is that you can actually solve these levels with Pwn tools. Maybe this is crazy, maybe this is easier for you. Yeah, go for it. Mm-hmm. Mm-hmm. Yeah, exactly. A char star will just be like a sequence of bytes. So yeah, you could represent your shellcode using a char star. Yeah. Yeah, so if you do like import or context arch equals this, and then do like pwn asm move rex 42 move RDI 3 ret or something, or like maybe then you want to do like move R10 some address, and then like call R10 and then ret. Let's say your shellcode looks like this, which is complete nonsense, but just for demonstration purposes, this will give you a string. I think you should be able to just basically in C write char data, or maybe we want to be more specific, shellcode equals, and copy the inside, and just do that. And then maybe you'll do like a write open proc pwn college 0, and then we want to pass shellcode, and then I don't know, let's say we're going to have written 30 bytes here. Maybe that's 30 bytes. You can do a str length on it or whatever, or figure out its length somehow, and then you could do like that. Yeah. Yeah, that's not an issue. C and Python are 99% sure going to be fine on this intermixing like slash, because this is basically just an escape as the I guess it would be the compiler interprets this string. It'll see this /x and say like, oh, we want a hex represented C7 to become our next byte, but it doesn't see an escape character here. It just says, oh, we want ASCII H as this byte. If you want to maybe not intermix this ASCII with hex represented data, something you could do is if we take our shellcode and assign it here, we can do some Python magic to make something happen. Maybe I shouldn't just completely jump to the punchline on how this will work. So something we can do is hex 42, which will print to us a string representation of hex 42. And we might want the last two characters of that, which will give us 42. The issue is that when we do this, if we do 1, this clearly is not 0, 1, which is what we wanted. So what we actually need to do is we need to get rid of the x. If we get rid of the x, that means we'll at least have 1, 0 on the left. This is just kind of something I've picked up over time in terms of making this a /x string or whatever you want to call it. We want to replace x with this. So now it handles the edge case of small values. So now if we bring this all together, and we want to do join, we'll turn it into an x string or an f string to be extra crazy. We want // to make sure that this is just a single backslash that doesn't get interpreted, because otherwise if we did single /x, it would get interpreted and get confused. And then we can do curly braces to inject this into our f string and be insane. And then we can do for e in shellcode. And if this makes you happier so that you don't have ASCII in your string, you can do this. But ASCII should be just fine. No, it shouldn't. And something I was going to point out is if you maybe want to be crazy and use pwn tools to solve these levels beyond just generating your shellcode, but to actually like scriptably solve these levels, something you can do is say process equals pwn.process on launch. Why not? It's just a process. This will start up process. If we read, let's say 4096 bytes and print decode Latin in case anything's crazy, we can see that the process is starting up. We're getting somewhere, still going, lots of intro stuff. In fact, we could actually just go all the way until maybe like this welcome to pwn.college thing. If we, no, we don't want to exit. If we want to say restart it or whatever, process equals this, and then we can just do process receive until that. Something went wrong. Oh, is it because we had the old process still running? Probably. I don't know if we can kill it at this point. Let's take a look. The issue is that this was probably wanting to bind to a port, and it can't bind twice. So we'll just kill it. Oh, maybe that didn't quite kill it, did it? It's not happy. Kill that one too. So we're in practice mode. I don't know what's going on with this defunct process, but we'll just let it chill and hopefully it doesn't get in our way. Let's go foreground process equals this, receive until that, which will take a few seconds, and I guess in this case prints because we're in IPython. And then you can really just do whatever you want. You can do, for instance, send line. You could do echo, and then we need to do double backslash if since Python will interpret one of these backslashes, and if we do backslash, it basically just says, hey, we actually just want a single backslash. And we could write this to pwn.college, and we can do process.read4096 to see what came back. Oh, we forgot a -ne. We can see that the kernel crashed in this case. Something to pay attention if you do this method is that you're actually going to get back what you send, because we are interacting with this terminal. What's the right word? Basically, we're getting the raw data of this terminal, and terminals echo back to you what you send to them in order to display it on the screen. So even though we sent it this, it actually echoes it back to us to tell us to print this on the screen, basically. And you'll also notice that instead of just using \n, terminals use \r/n in order to, because these are basically all just terminal ANSI codes, or I don't even know if these are the ANSI codes necessarily. These are all just terminal codes, like \r basically says go to the beginning of the line, /n means go down. So this is literally like the raw data of the terminal telling us what to do. So you have to handle the fact that we're getting stuff echoed back, but you can work with it. I don't know, maybe you don't want to do this insane thing. Maybe you just want to write C. But the other thing you can do, of course, is if you need to write C, and maybe this is, as I said, insane, you can write kernel.c write as F, and then you can do like f.write. You can really do whatever you want. You could do like F multi-line string. You can just start typing your C. What we would want here is, let's just do a very simple thing. Let's do like ints main. Actually, since we're in an F string, we need double curly brace to escape the curly brace. And then we can do like car data equals shellcode. We need a semicolon. Yeah, let's just stick with this. Actually, we also need to quote this. And then let's just end that. Sure, why not? Let's do that. And then, oh, this doesn't know about that. Home CTF. Now, of course, if we look at the file we just created, it's going to look a little weird because it's going to have extra indents. You could dedent this if you really cared about that, but C doesn't care. Okay, what did I just do to my mouse? Whatever, we'll deal with it later. And then, oh, I guess this is probably not a great idea because we can see that our byte string is actually getting in there. So maybe what we want to do is decode Latin to make sure it's just a string and doesn't get interpreted as a byte string, and then its repr go in. Then we can cat home ctf kernel.c, and maybe this is especially insane, but maybe C can handle it. Otherwise, we can take our previous thing that we showed of doing this, and we can do shellcode encoded equals that. And then maybe instead we just write shellcode encoded here. Encoded. And now if we cat home ctf kernel.c, we can see that we got our C file that we're starting to build up. And of course, you'd want to do your open and write syscalls after this and whatever else you need to do. But from here, we can just do import subprocess. And then you can do subprocess.run, gcc, static, home ctf kernel.c -o kernel. Cannot open. Oh, we're about to put this in our not in our current working directory. We want to put it in home CTF. Okay, so now if we look at home CTF kernel, we just compile this binary. In fact, maybe something we should do instead is like puts hello world to show that this is running, and recompile. Yeah, but that should be fine. And then what we can do is, do we still have our process running? Nah, it died, didn't it? Process, make sure it's dead though. Process kill, process equals launch, receive until, and there we go. And then we can do send line this, but instead of that, maybe what we want to do is just run home CTF kernel, which is that binary we just produced. Yep. And then let's read 4096. And we can see that our hello world got printed. So maybe this is not worth the hassle. But if you really want to script these challenges in the same way that you've been doing over the last several modules, you can in fact just interact with launch. Okay, are there any more questions before I start to wrap up this office hours? Three. Yeah, so the description of the challenge, which is definitely useful because there's not actually shell coding in level 3. If we SSH in, we can see what the description tells us. So if we run launch, and this will only print in the teaching challenge, but of course the testing is going to be the same high-level overview of what's going on, with maybe a different address or whatever. It will tell us that the character device will allow you to call an arbitrary function inside the kernel. So we're not actually able to call arbitrary shellcode, but it will just call some address. And you'll have to figure out, kind of maybe looking at it in GDB, objdump, whatever, to see exactly how that works. But if we also look at symbols, actually it also tells us here in the line above, the kernel module defines a win function which will log the flag if called. So we can confirm that this win function exists if we tail proc k all sims, and we can see that there is a win function defined here that will basically do this similar style logging of basically giving like a timestamp and then whatever you sent it. Okay, are there any more questions? Mm-hmm. Yeah, so we don't have it completely planned out, but yeah, it'd probably be reasonable to expect some buffer overflows in the kernel leading to potentially shellcode, or buffer overflows leading into ROP in the kernel. We've still got some more modules on heap exploitation, so maybe there will be some heap related exploits inside the kernel. And there's also a module on race conditions, which is actually very fitting for the kernel. A lot of maybe a new person writing a kernel module that doesn't exactly know about a lot of security implications could easily fall into the trap of introducing race conditions in their code. So if you think about it maybe from like an operating systems course where you need to use like semaphores and stuff in order to make sure that data doesn't get read/write in the wrong sequence. So for instance, if you have two threads running that are just incrementing some variable without semaphores, and each of them runs 1,000 iterations, you'd probably expect that, and it starts like, let's say at 0, you'd probably expect that I will be equal to 2,000 at the end, but due to race conditions, I can very easily be a smaller value. I don't think it can be a larger value. I think it could only be a smaller value. But that's kind of the idea of a race condition, and those sorts of things have all sorts of security implications, and they very naturally fit into the kernel, because the kernel has all sorts of resources, and generally a race condition is a kind of improper concurrent access to a resource, kind of how to think about it. And the kernel having all sorts of resources is kind of a very nice place for race conditions to pop up. So we'll probably have some of those as well in the toddler 2. All right, I am going to wrap up my office hours then. Thank you everyone for joining me. Feel free to message in the help channel if you have more questions, or if it's a very specific sort of question, you can also message me on Discord, or you can send us an email. All right, see you everyone.